In this video, let's do an example to cover the substitution method known as reduction to separable variables. Now recall that the way that this method works is that, let's say you have a differential equation of the following form, first order, where the right side is a function of ax plus by plus c. The idea is that you let our substitution variable u equal ax plus by plus c, and then by doing that, your equation is able to reduce to a separable variables problem. So in our example, we see that the denominator is of that form, ax plus by plus c. So following that, we let u equal 3x plus 2y plus 5, and similarly, we can also have u minus 5 equals 3x plus 2y. The reason we solve this is because in the numerator, we see that. Now, if we take the derivative of u with respect to x, we get this. Obviously, the dx over dx cancels, and then we get this. It simplifies. If we solve for dy dx, we get this. And plugging in, obviously, in this, our equation becomes the following. 1/2 du dx minus 3/2 equals u minus 5 over u. Now, for brevity, I will just rewrite the du dx as u prime, and then I will distribute the u over the denominator. Next, I will add the 3 over, so it becomes 5. Now I will re-expand the u in the denominator. And rewriting the u prime as du dx, we see that we have successfully reduced this to a separable variable. So now we can separate. Let's bring the u's and the x's on opposite sides. We integrate. And then upon integrating, the first thing we can do, by the way, before we can actually integrate this, is we can multiply a 5 on both sides. That turns the denominator into u minus 2 on the left side. Now what we do next is we're going to do a u sub, where if we let v equal u minus 2, we can see that dv equals du, and similarly u equals v plus 2. Plugging all those in, we get the following. It becomes in terms of v. Now we distribute the v over the denominator, we get. Now we can integrate, and it becomes v plus 2 natural log of v equals 5x plus c. Using the natural log property, where the constant on the outside becomes a power, we see this, v plus natural log v squared equals 5x plus c. Now we take e to the power of on the each side, and splitting it up, we get this. Now you may have noticed that e to the c became a constant c because it's just a constant. Now the e to the natural log can cancel out because they undo each other. So we get the following. V squared e to the v equals c e 5x. We can plug back in for v, we get the following. And then similarly, we can plug back in for u, and we get the following. Now let's clean this up. First off, we can see that the 5 minus 2 becomes a 3. And next, we can see that we can split the exponent into the following. So we have e to the 3x times e to the 2y times e to the 3. The e to the 3 is essentially, it can be divided over and be incorporated into the constant. And further, the e to the 3x can be divided over. Now remember that when you have e to the in the numerator and e to the denominator, and the power is of the same term, then you can just subtract the powers. So we get the following, which was e to the 2x, which was 5x minus 3x. And now we divide the e to the 2x over to keep this constant by itself. And now we can realize that every term on the left side is raised to a power 2. So if we take that power 2 out, then we get the following. And now if we take the radical on each side, then we will get this. Obviously the radical of a constant is a constant. That's why you see a constant. And using the rule that we had earlier for taking the quotients of powers, I have e to the y minus x on the left side. And this right here is our solution. Now let's clean the slate so we can analyze this. Now obviously in the denominator, 3x plus 2y plus 5 cannot be 0. In other words, 2y cannot be negative 3x minus 5. And then in solving for y completely, we see that y cannot be negative 3/2 x minus 5/2. This right here is what we call a singular curve, meaning any points on the graph that cross this curve, the solution does not exist. Okay? Now let's go ahead and generate the slope field. Now the solution, by the way, looks like this. Right now the constant is set to -100, but let's say if we were to slide the constant, we can see how it fits along the solution curve. Now it's at 0, or actually it just crossed 0 and it's going back to 100. So we can see the kind of pattern that this follows, that at constant equals 0, the solution, let's set it to 0 right here, it's a straight line, and which actually follows, because if c became 0, then e to the y minus x would become 0, and essentially it would just be the line 3x plus 2y plus 3. So this sort of follows along with that logic. But now if you go, we can see how it goes towards the right. As c is getting positive, you can think of a positive exponential, e to the y minus x. But as c is going negative, you can think of the exponential becoming negative because c is negative. I hope that kind of makes sense. Now if we bring the singular curve into the mix, let's do that, we see that it is this dotted line. Now basically anywhere where this curve crosses this line, the solution doesn't exist. So for example, in this scenario, at this point, the solution would not exist. Okay?